Rational numbers can be written as a ratio form P by Q, where P and Q are integers and Q not equal to 0. Then what about the numbers that cannot be written like this? They are called as irrational numbers. Numbers like root 2, root 3, pi and 0.101, 1011, 10111 are examples of irrational numbers. Such numbers were first discovered by Pythagoras, who also created the famous Pythagoras theorem on right angle triangle. That is, in a right angle triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides, which are the base and the perpendicular. So, c square equals a square plus b square. This theorem will be useful to locate irrational numbers such as root 2 on the number line. So, let's locate root 2 on the number line. According to Pythagoras theorem, c square equals a square plus b square. Let's see which is the hypotenuse p equal to root 2. So, c square will be equal to 2, which can be written as 1 plus 1, which is same as 1 square plus 1 square. So, the length of the other two sides are a equals 1 and b equals 1. Now, draw the right angled triangle on the number line with the base starting from 0 towards right. The length OA will be root 2. To locate it on the number line, using a compass with center O and radius OA, draw an arc intersecting on the number line on point P. Thus, point P corresponds root 2 on the number line. Now, let's talk about real numbers. Real numbers is a combination of rational numbers and irrational numbers, and that is denoted as R. So, every real number can be represented as a unique point on the number line. So, a number line can be called a real number line. Let's see rational and irrational number from a different point of view, that is in its decimal expansion. So, let's first see what decimal expansion is. It is the form of a number that has a decimal point, either actual or implied. Examples: 10.2 or 0.0084 are actual decimal points, and implied decimal points are whole numbers like 17, which can also be written as 17.000, etc. Now, let's find out how to convert a rational number into its decimal expansion. Consider the number 7 by 8. We need to divide 7 by 8 by long division. We mention 7 in its decimal form and divide it until we get the remainder 0. So, the result is 0.875, which is the decimal form of 7 by 8. Such type of decimals are called terminating, as we can complete the division process. Next, let's divide 10 by 3. Here we notice that we never get 0 as remainder, and the digits continue to form after the decimal point, and also those digits are repeating. Such decimal numbers are called non-terminating, recurring or repeating. And here we notice that 3 is repeating. So, we can write 3.333 etc. as 3.3 with a bar on top of 3. That is, bars are used after the decimal point for repeating numbers. Similarly, we can convert any rational number from P by Q form to decimal form by long division. For example, 1 by 7 equals 0.142857 bar. Here, the digits with the bar are repeated. And next, we have 512 divided by 1000. For this, even without performing the long division method, since the denominator is 1000, that is the third power of 10, we just need to shift the decimal point of the numerator value 3 digits to the left to get the answer. Now let's convert rational number from decimal form to p by q form. For terminating decimals like 3.58, since there are two digits after the decimal point, we multiply and divide the number by the second power of 10, that is 100, and then simplify it. For non-terminating recurring decimals, for example, if we want to convert 0.168 bar, since there are 3 digits of recurrence, we divide the number without its decimal point by 3 nines, that is 999, and simplify it. And if only 68 is repeating, as only one digit after the decimal point is not repeating, shift that decimal point to one digit right, that is multiply the numerator and denominator by 10. Then for the repeating digits, after removing the decimal point and bar, we divide them by 2 nines as the repeating digits are 2 and simplify it. Now let's find out decimal expansion of irrational numbers. Let's consider the value of pi. Pi is equal to 3.141592 etc. and the digits continue after the decimal point. Also, there is no repeating pattern of digits. Such numbers are non-terminating, non-recurring or non-repeating numbers. Another example is root 2, which is equal to 1.41421 etc. Now we see that root 2 is between 1 and 2. So we can find many irrational numbers as well between any two numbers. Let's find out how it can be done. Let's see an example. Find an irrational number between 1 by 7 and 2 by 7. We find the decimal forms, that is 1 by 7 is 0.142857 bar and 2 by 7 is 0.285714 bar. Now easily we can find non-terminating, non-recurring decimal numbers lying between these two values. For example, 0.160, 1600, 16000 etc. So we can conclude that when we create the decimal expansion for real numbers, for rational numbers it's either terminating or non-terminating recurring, and in the case of irrational numbers the decimal expansion is non-terminating, non-recurrent.